Let's take a look at taking the derivative of functions that look like this, where they have a constant or some number as a base, and the exponent has a variable, or the function of a variable. First, let's take a quick look at memory lane in our exponents. We know when the bases are the same that we can add the exponents together when the bases are the same. So this is 3 to the x times 3 to the x is 3 to the x plus x, which is 3 to the 2x. When we look at the one on the right here, those bases are the same again, so we can add these together, 2x plus 3x, so that gives you e to the 5x. Okay, so that works out really well. And let's now go down below. Here, this is a superpower. We have this 2x is e to the x raised to the 2x power. That means we are going to multiply those exponents. So we get x times 2x. Each of those x's have a variable exponent of just 1. So that gives us e to the, make him an exponent, 2x squared. Now when we look at the next one, we have a base of 2 in the numerator and denominator. So let's go ahead and move this term to the numerator, and we're going to negate that exponent then, and that gives us 2 to the 3x plus 1 times 2 to the negative x. Now we have like bases, so we can add those exponents together, and that second one is plus a negative x, so that gives us 2 to the 3x minus x is 2x, and then the plus 1. So those are our exponent rules. We're going to need those. When we look at derivatives of functions that are exponentials, when the base is an e, his derivative is just e to the x. Now, if that function in the exponent is a function that isn't just an x, then we get, keep it exactly like it is, and then chain rule out the derivative of that exponent. So this is your chain rule embedded inside of this. When you have a number that's a base a, over here, at a base a that is not e, and we get then the natural log of the base times, keep it exactly the way it is. Now again, the issue is if that exponent is a function, we still get the natural log of the base. We still keep the function exactly as it is, but now we're going to take the chain rule and multiply out the derivative of that exponent. So we have to be careful if the exponent is not just a single variable. Now remember, when you're looking at pi and e, those are just numbers. So if we take the derivative of e squared, pi squared, just like the derivative of any number, the derivative is 0. So watch out for those. They're not variables. Here are some examples for you. We're going to use the sum and difference rule, the power rule, and our new rules as well. This guy, power rule, this guy's a constant, his derivative is 0. This is going to use our new rule. 3 comes along for the ride. Derivative of e to the x is just e to the x. Derivative of x squared plus 2x. Derivative of 5 is 0, so we just leave him. For the next one, the first term, e to the x, derivative is e to the x. Now, this is a variable raised to a number. So we're going to use the power rule. It's going to look a little different. If that was x to the 17, you would say his derivative is 17x to the 16, because we subtracted 1 from the exponent. So we bring the exponent down, keep the base, subtract 1 from the exponent. Looks really, really weird. But that's a number. Bring it down and then subtract 1. It's just the power rule. Now this guy, e to the e, is the same as if you're saying 17 to the 17 is a number. The derivative of a number is 0, so we don't have to write plus 0 here. Next term, this first one, we are going to use the product rule on that. So it's the derivative of the first, derivative of x is 1 times the second, plus the first times the derivative of the second, e to the x is e to the x. And then now we go to the second term. All of this comes from this guy here. Now we're going to take this derivative of e to the x is e to the x, and we can leave it like that. Now we finally get to one where there's a function in the exponent that has a derivative that isn't 1. So the 3 comes along for the ride. We rewrite that function as e to the 2x plus 5, and then we chain rule derivative of the exponent. Derivative of 2x is 2, derivative of 5 is 0, and this can be rewritten that 2 comes out front, 6e to the 2x plus 5. Two more for us. Here's another one that has a function in that exponent. So the derivative of e to the x, or e to anything, is just rewrite it. So x cubed minus 5x, and then we chain rule out the derivative of that exponent. X cubed gives us 3x squared, minus 5x gives us minus 5, plus x cubed, derivative of that is 3x squared, minus 5x, derivative of that is minus 5. So we got a derivative piece for each term. Now for the next one, we have two terms multiplied times each other. So we're going to use that same language. Derivative of the first, 6x squared, times the second, he comes along for the ride, plus the first times the derivative of the second. Well, what's the derivative of that exponential? It is going to be, keep it exactly like it is, chain rule out, what's the derivative of x squared, 2x. Now sometimes we leave those alone. It depends on what you're doing this for, exam, quiz, or an online homework system. And so we could collect those constants here where we take the 2 and the 2 to get 4. So let me show you where these are coming from. This 2 and this 2, 2 times 2 is 4. And then x cubed times x to the first is x to the fourth. And then we have the last piece, e to the x squared. And that's it. Hope you're having a great day.